My name is Klidos. I'm an assistant professor at the University of Nicosia, and we have been doing blockchain education since 2014. And this is part of the research project that we have been doing and started this back in 2019 when we have been simulating the behavior of the RPCA consensus algorithm. We have been trying to understand the behavior of the algorithm. As you know, RPCA, it uses an neural list to define the quorum of validators that are trusted within the network. And as part of and continuation of our work, in this particular paper, we will be analyzing and assessing the performance of the blockchain benchmarking framework that we proposed last year. So basically, we proposed the blockchain benchmarking framework. We defined the design considerations of this blockchain benchmarking framework. We call it BBF for easiness. And in this paper, which is a continuation of this job, we will be assessing the efficacy of the BBF in assessing the design decisions of consensus algorithms, blockchain protocols. As you know, the emergence of the blockchain trilemma has kicked off and triggered the implementation of many different blockchain protocols with many different blockchain design considerations. And we've seen how blockchain networks have been trying to resolve the blockchain trilemma. Every blockchain with its own different way. We've seen different blockchain protocols trying to be more decentralized and scalable, compromising security. We've seen other blockchain networks to be more secure and scalable, compromising decentralization. And we've seen others kind of being more secure and more decentralized, but kind of compromising scalability. So, and if you have been trying to understand the design specifications of each blockchain benchmark and blockchain network, you will understand that there are many complexities understanding the design specifications of each network, and there are many, many challenges. Even the simplest case, if you would like, for example, to spin up a private network in a controlled environment and configure it in order to do more experiments in a controlled environment and improve the algorithms, et cetera, you will see that this is a challenge, and even for educational purposes. So this gives us an idea to propose our own blockchain benchmarking framework, and what are the standards that this BBF should look like, and what kind of things we can do in terms of empirically assessing different blockchain implementations. So what we did actually, we standardized the design of a BBF. As I mentioned, there are several motivating facts, such as, for example, it is very difficult to configure a network. It is even more difficult to try to simulate kind of attacks or even validate the specification that has been drafted in a white paper. For example, to validate the design decisions that the specifications are trying to expose in the white papers. So we are trying within the blockchain benchmarking framework to define those specifications and run several experiments in a standardized way. What we did actually, we created a very modular design of a BBF that allows actually the deployment of any type of a blockchain network. And then there are standard templates that could be used for defining various types of attacks, for example, like, for example, double spends or Byzantine faults. And then through the blockchain benchmarking framework, you can also monitor the behavior of either the consensus algorithm or the network in general. For this particular paper, our aim is not to have a head-to-head comparison of the networks, but better to understand the mechanics and the design, if you like, considerations and the design complexities of each network. So it's a matter of understanding their mechanics. And with this particular work, we wanted to assess the efficacy of the BBF. So does it make sense to use a standardized tool for performing such kind of evaluations or benchmarks? So before we run into the experiments that we have decided to conduct in order to understand the efficacy of the protocol, let's look at the architecture, the high-level architecture of the protocol. of the framework. So basically we have a modular design where we are exposing the services of the BBF through REST APIs. We have at the lower level the interaction with the blockchain backbone. So this is where you can configure the network. You can spin up a private deployment of a network. We are supporting XRPL, Stellar, Hyperledger Besu, and Ethereum. We have 2 clients of Ethereum. One is configured using proof of authority, and the other one is configured using proof of work. But as I mentioned previously, the BBF is extensible. We provide open source tooling and a template that you can extend it to support other networks as well. So at the upper level, we have the benchmarking engine. So in the benchmarking engine, we have defined tools for issuing transactions. So you can define, you can draft transactions, sign them, and send them over to the network. We have also what we call the UNL manager, which is particularly drafted for the RPCA. We have also a traffic generator and wallet management that allows the user to manage wallets and private keys. On top of that, we have a monitoring engine. So basically, monitoring engine scraps data from the clients, because here we are not doing simulation. We are doing close to real simulation because we are using the actual clients of the of the protocols themselves. So basically, our monitoring engine comprises of a push gateway that scraps data from the clients, send them to an InfluxDB, and from where we can understand insights and look at the various trends concerning latency, throughput, and consensus efficiency. And on the top of that, last year we proposed an interface that allows us to deploy BBF as a web service, and is currently available. It is not that concurrent to support many users, but you can visit the website and you can start your own, let's say, synthetic scenario of understanding the behavior of the blockchains that we support. So as I mentioned in this paper, we're trying to understand whether the BBF that we proposed, that we standardized, makes sense. In order to do that, we have decided to use a couple of use cases and try to validate the design decisions of the protocols in test. So we have instantiated BBF using the XRP ledger, and we have been trying to understand 2 design decisions of the protocol. The first design decision is to use, for the RPCA algorithm, is to use the sequence number in order to prevent double spends and maintain the order of transactions. The other design decision is to validate the percentage of tolerance of the network, of the RPCA algorithm, in terms of tolerating malicious transactions, malicious nodes that are participating in the UNL list. So we did the same for Ethereum, and we have instantiated Ethereum using the proof of authority algorithm. So again, how to validate the decision of the network on preventing double spends and how those double spends are prevented, and for the consensus algorithm to understand whether the consensus algorithm it meets the minimum criteria of maintaining resilience in the presence of faulty nodes. So in order to do that, this is a blockchain benchmarking network. You need to be able to define those attacks so that you can later on create your synthetic scenario and then use those synthetic scenario to stress test the protocols. So as I mentioned previously, the framework is quite general, which means that you can create your own definitions of attacks and then inject them through the protocols under test. So the first attack that we're kind of simulating, injecting here, is double spends. So as you know, transactions are not final, most of the networks, so finality takes a bit of a time. So this gives a time window for the attacker to attack the network and double spend. And the second kind of attack that we are injecting and defining through the BBF is fault tolerance. So how the network reacts in the presence of faulty nodes. So we're trying to simulate these types of failures, either faults or Byzantine faults. As I mentioned previously, we're using the real client here. The platform, actually the framework is using Docker engines and the Docker engine and Docker containers to run the clients in a close to real environment. So for the XRPL, that was our first use case. What we did in order to validate the design decision of the RPCA algorithm to use the sequence number in order to prevent double spends and maintain the order of transactions. So what we did, we spin up a network of 10 validator nodes as a full mesh, which means that every node is connected to each other and they share the same UNL list. What we did then, we used the toolkit to craft transactions and then ship them to the network. We crafted thousands of transactions using the same sequence number, and then we ship them to the network, and then we use the monitoring tool to see the behavior of the RPCA algorithm, the consensus algorithm that is being used by the XRP ledger. And we validate that the RPCA algorithm is actually rejecting those transactions. The validation happened as follows. Basically, before we send each transaction, we sign it off, and then we hash that transaction. And once we shipped it to the network, we then monitored which transactions have been rejected, and we have recorded the hash. We then compare with the transactions that have been duplicates, and we've seen that correctly the RPCA consensus algorithm rejected those transactions. Now, for the faulty nodes, what we did actually, we wanted to validate again the design decision of the RPCA to maintain the minimum overlapping degree for the nodes that are participating in the UNL list. So according to the specification of the protocol, RPCA needs to maintain about above 90% of overlapping in order for the network to be resilient. We have stretched this to 80%, and we have seen that still, also at this boundary, the network remains resilient. And we have validated that with the BBF as well. We then repeated the experiment using the Ethereum deployment. So we deployed a private Ethereum network using Hyperledger Besu, and we have used the proof of authority algorithm. It was much more convenient for us so that we do the testing. And as I mentioned previously, our purpose is to validate the efficacy of the BBF. Does it make sense to use our toolkit to run these kind of experiments and validate the design decisions and specifications of the protocols? So in order to kind of simulate double spends for this instantiation of Ethereum, what we did actually, we created a network of several nodes, let's say n nodes, and we split the network into two segments. We then use the toolkit to sign off transactions from the same wallet using the same private key and try to double spend. At the time that the transactions have been submitted, we then merge the network back to the unified network, and we have then been monitoring how the proof of authority algorithm behaves in terms of rejecting the double spends. It performed really well as it's supposed to be, and we have showcased that our BBF could be used as a toolkit for assessing those kind of design considerations of the protocol. Now, for the faults, what we did actually, we have implemented a synthetic scenario, again using the BBF, to randomly inject faulty messages to the messages that have been sent by the nodes. And we have also randomly disconnecting nodes from the network, at the same time of sending various transactions using the toolkit. As I mentioned previously, we have the tools using the BBF, which is open source by the way, And I will be sharing the Git repository for everybody to look out. We have been doing that by also sending transactions and disconnecting nodes, sending faulty messages, etc. And we have been looking at the behavior of the network. We've seen that although the throughput of the network was quite a bit low, the network managed to overcome double spends, and we have stress tested this to more than the 30%, let's say, that the consensus algorithm was able to cope with. So what we have been trying to do with this work was actually to evaluate whether the BBF that we proposed makes sense and could be used for assessing and understanding the behavior and then design specifications of each blockchain protocol. It is not about a head-to-head comparison of those different protocols, but more like understanding their mechanics. As I mentioned previously, each protocol is unique in its own way. So this is an upcoming paper that will be published in IEEE as a continuation of our previous paper that was the definition of the BBF that was published in IEEE Access. We have also deployed the BBF as a web service on AWS, which is not that concurrent, so most probably it's going to break if a lot of people are using the service, but just as a proof of concept, you can join the service and use it to spin up a private control environment of nodes and then inject various attacks in the network. That's all from my side. Thank you so much.
We have time for questions. Any question from the room? I have one question for you. Could the BBF, the framework, could be used to make recommendations for industry stakeholders who are always coming with the same question, which blockchain for my use case?
Actually, one of the reasons that we have implemented the BBF is because usually developers, decision makers, even people that they would like to teach such networks, they don't know from where to start. They don't know which network is suitable to their use case. And we've seen, due to the fact that those networks are built by the community, there is a lot of broken documentation out there, and it is, even for developers, experienced developers, it's very hard for them to configure those networks and understand the specificities of them. So we wanted to provide a tool to the community that it will allow anyone to do such assessments and understand the specificities and then understand whether this is the right blockchain network to use or not for a particular use case. So yes, good question.
Yes, question in the back.
So you mentioned when testing the performance of XRP Ledger, you used a full mesh network.
Yes.
I might have misheard. What size of the network did you use?
So in this particular example, basically we used 10 nodes.
Right. And then a follow-up question, is there a particular reason why you used a full mesh network rather than some kind of a different topology?
Yes, not a particular. It was much more easier for this kind of experiments. We just wanted to validate a specific design requirement, so it was not a particular reason. But it could be used for other, configurations of the network. Yeah.
Great. Thank you.
Thank you.
Last question from me. How hard would it be to expand to other consensus and other chains?
As I mentioned previously, the way that we have designed the framework is very modular. There is a template, which is actually a way to structure BBF to support more networks and configuring the client and adapting the client to work with the BBF that we are currently proposing. It needs a bit of technical work, but it is easy to do because you will be following the guidelines and the standards that we have already proposed.
All right, we'll conclude here.
It's upcoming, I think next year.
Is that appropriate?
Yes.
Thank you so much, Klitos.
Thank you so much.